Alright guys, let's continue with this question from 2024 A-Levels Paper 2, Question 2. Okay, part A says ideal gas consists of particles in constant motion at high velocity. It's assumed that there's no IMF between gas particles in an ideal gas. Okay, so this is one of your ideal gas assumption. They want you to state two other basic assumptions as applied to an ideal gas. So the first one could be saying that they have negligible gas particle, have negligible volume, okay, and then perfectly elastic collision. All right, so that is the first question. Just recall. Okay, then the second part of A, right, says that a real gas behavior, for example, nitrogen gas, can be compared to the behavior of an ideal gas. Okay, so this figure below here shows the values of PV over RT produced for nitrogen gas. Alright, so they say on this same figure, sketch the relationship for an ideal gas. So usually they will give us the ideal gas and ask us to sketch this for the real gas. But for this question, they gave us the real gas, and then for ideal gas, it's just one straight line like this. Alright, so for 1 mark, drawing one straight line seems pretty reasonable. Part C, they want you to explain the non-ideal gas behavior of nitrogen at very high pressure Z. So Z, very high pressure, we're talking about here at this point. So you can see that actually there is a very positive deviation. Your answer should not refer to IMF. You should not refer to IMF. You may find it helpful to refer to this figure 2.1. Yep. Okay, so if your pressure is very high, right? When you have high pressure, okay, the volume of the size of the particle, right? The gas particle becomes significant. Okay, the volume of the gas particles becomes significant. Okay, because we have already listed it out as the one of the basic assumptions. So this assumption is no longer true. That's why it deviates positively. All right. So because this graph is basically your PV over RT, so when your volume of the gas particle become very big, right? So i.e. your volume here, your V, actually now becomes very significant on top of the volume of the container, right? So that's why it results in a positive deviation, right? So this is why it results in a positive deviation. Okay, so that's for part C. Then the last part, this is a pretty short question. Nitrogen gas behave as a non-ideal gas at moderate. So this time round, it is a moderate pressure, W, because at this pressure, the intermolecular forces are not negligible. Okay, so basically we are going to talk about IMF lah, at moderate pressure W. Okay, moderate pressure W here. Okay, so you can see that there is a negative deviation. Means that it's lower than ideal gas because of what? Okay, so they just tell you that N2 and CO have same volume for the molecule. So you don't need to talk about the size of the particle. Anyway, at moderate pressure, it doesn't really come into play. So they are telling you you can ignore it. Okay, they say that they have the same temperature, so don't need to talk about temperature. Then they say at pressure W, right, the approximate value is lower for CO compared to. So they want you to explain the negative deviation. So this part here, they want you to explain negative. Okay, let me just shift this over. They want you to explain negative deviation. Okay. Right, so you need to reference the all types of IMF. So what types of IMF is present in nitrogen gas and CO? Both of them have ID for both. Right, then since they have the same volume, right, so their ID is kind of like the same, right, for these two, but only CO has PD, permanent dipole. So this will be a more significant attraction. Significant IMF. Okay, for the attraction between your molecules. Alright, so that's why after the molecules of CO collide, right, is no longer elastic. Collisions, not elastic. Elastic, no S. Okay. Okay, so if it's no longer elastic, then that's why there is a negative deviation. Okay, so that is for 3 marks. Yep, we do not need to bring in any other types of IMF, just ID and PD. Okay, anyway, I think we should add in PD is stronger than ID attraction for molecules having the same size. Okay, that's it for this question.